Picture sending a message to someone you can see but will never be able to reach, watching them across an unbridgeable distance, studying them, learning about their history from the light they send your way. Your transmitter could be the most powerful device ever built, your signal focused with precision that would make engineers weep with envy. And you could wait for eternity, but that message would never arrive. Technology is not the problem, and the distance alone is not the barrier. The fabric of space between you stretches faster than any signal can cross it, which means everything you might want to say would be lost before it traveled halfway. This describes reality, not science fiction, and it defines your relationship with roughly 95% of everything visible when you look up at the night sky. We live inside what might be the most elegant prison ever conceived, a cage made not of bars or walls, but of expanding space-time itself. The observable universe stretches approximately 46 billion light-years in every direction, a sphere of light and matter representing everything humanity has seen or could hope to see, around 4.35 times 10 to the 23rd power kilometers, or about 2.70 times 10 to the 23rd power miles. Numbers that large lose all meaning without careful anchoring. Of all that cosmic real estate, though, all those hundreds of billions of galaxies containing hundreds of billions of stars each, we can only ever hope to reach, influence, or communicate with roughly 4 to 5%. Expansion has already placed the rest forever outside our causal future. Not because we lack ships or time, but because the geometry of space itself forbids it. That is what this video explores. One of the most unsettling discoveries in modern cosmology turns out to be that two very different boundaries define our place in the cosmos, with one telling us what we can see and the other telling us what we can ever touch. The gap between them reveals something startling about existence itself. By the end, you will understand what it truly means for space to expand, why distant galaxies can recede faster than light without violating physics, how two different cosmic horizons create a strange asymmetry between observation and action, and why accelerating expansion driven by dark energy slowly shrinks the sphere of our possible influence. If you appreciate this kind of deep, patient exploration, if you value taking time to truly understand rather than skimming the surface, consider subscribing to the channel, which helps these explorations reach more curious minds and tells me this content resonates with you. Now, let us begin. Starting with something that sounds simple but actually requires careful thought helps here. What do we mean when we say space is expanding? Most people picture something like an explosion when they first hear this phrase, imagining galaxies flying outward through space like shrapnel from a cosmic bomb, racing away from some central point where everything began. The picture is intuitive but deeply misleading. Expansion is not about objects moving through space, but about space itself changing. 1915 brought Albert Einstein completing his general theory of relativity, a framework that reimagined gravity not as a force pulling objects together, but as the curvature of space-time caused by mass and energy. Isaac Newton had successfully explained solar system dynamics for over 2 centuries with his inverse square force description. But Einstein's theory suggested something far stranger, that the geometry of space and time themselves could bend, warp, and change over time. Within a decade of that publication, mathematicians and physicists found solutions to Einstein's equations describing a dynamic rather than static cosmos. Between 1922 and 1927, Alexander Friedmann and Georges Lemaitre independently developed mathematical models showing that the scale factor, essentially measure of cosmic distances, could increase or decrease over time, not as idle speculation, but as rigorous solutions emerging from general relativity's mathematics. Observations came next. 1929 brought Edwin Hubble, publishing a remarkable finding from his study of what were then called extragalactic nebulae, what we now know as distant galaxies. He found a relationship between their distances and radial velocities. The farther away a galaxy was, the faster it appeared to move away from us. This relationship, now called the Hubble-Lemaitre law, provided observational evidence that space was indeed expanding. The crucial distinction lies here, and this is where most intuition leads people astray. When we say a distant galaxy is receding from us, we do not mean it rockets through space like a bullet fired from a gun. The space between us and that galaxy stretches, and while the galaxy itself might sit relatively still in its local region, expansion grows the distance between us. Think of 2 dots drawn on a rubber sheet that you stretch uniformly in all directions. The dots move apart, but neither dot actually travels across the sheet. Both simply carried apart by the expanding surface beneath them. This distinction might seem like semantic hair-splitting, but it has consequences that change everything about our cosmic situation. Let me take you deeper into what metric expansion actually means, because this concept sits at the center of everything that follows and gets misunderstood constantly. Cosmologists talking about expansion refer to a specific mathematical concept encoded in the Friedmann-Lemaitre-Robertson-Walker metric, the standard tool for describing a cosmos that looks roughly the same everywhere and in every direction when you average over large scales, which physicists call homogeneous and isotropic. The metric contains a quantity called the scale factor, usually denoted by the letter A, which changes over time. Scale factor essentially measures the size of space at any given moment. And when we say space expands, we mean this scale factor increases. What does that mean concretely? 2 points in space that are not gravitationally bound to each other see their proper distance increase over time. 2 galaxies separated by a certain distance today, with neither pulling the other gravitationally, will find themselves slightly farther apart tomorrow. Not because either moved through space, but because the scale factor increased. And multiplying that factor by coordinate separation yields a larger proper distance. This is why physicists call it metric expansion, encoded in the metric, the mathematical object describing space-time geometry, with space between objects literally stretching. A detailed analogy might help crystallize this. Imagine a rubber sheet with a grid of dots drawn on it, each dot representing a galaxy. And then, Imagine stretching that sheet uniformly in all directions. Every dot moves away from every other dot. Sitting on any particular dot, all other dots appear to recede, and the farther away a dot sits, the faster it appears to recede. This matches exactly what we observe. No matter which galaxy you occupy, all other galaxies appear to move away, with recession speed proportional to distance, which is the Hubble-Lemaitre law in action. The crucial point is that dots in this rubber sheet analogy do not move across the rubber, but get carried apart by the stretching rubber itself. A dot might sit perfectly stationary relative to the rubber immediately beneath it, yet total distance between any two dots increases because the rubber between them expands. The same holds true for galaxies. A typical galaxy does not zoom through space at thousands of kilometers per second, but might sit relatively stationary in its local region of space-time. Space between it and us stretches through, and that stretching accumulates over distance. The Hubble constant tells us the rate of this stretching. At 67.36 kilometers per second per megaparsec, with an uncertainty of about 0.54 kilometers per second per megaparsec based on Planck satellite observations and cosmic microwave background analysis, this might seem like a modest rate. Let me unpack what that number means. A megaparsec spans about 3.26 million light-years, which means for every 3.26 million light-years of separation between us and some distant object, space between us grows at an additional 67 or so kilometers per second. At small distances, this is negligible. A galaxy 1 megaparsec away recedes at 67 kilometers per second, fast by human standards, but slow compared to light speed. At 10 megaparsecs, recession reaches 670 kilometers per second. At 100 megaparsecs, 6,700 kilometers per second. Extrapolate to truly cosmological distances and the math becomes astonishing. At what distance does recession speed equal light speed? Light travels at approximately 300,000 kilometers per second. If recession speed equals the Hubble constant times distance, then recession matches light speed when distance equals light speed divided by the Hubble constant, a distance called the Hubble distance or Hubble radius, which works out to roughly 14 billion light-years. Beyond the Hubble radius, objects recede faster than light, not because they travel through space faster than light, but because cumulative expansion of all space between us and them exceeds light speed. The metric stretches superluminally. Before revealing what that means, let me address the obvious objection. Did I just claim something violates Einstein's special relativity? Did I claim something moves faster than light? No. Understanding why requires appreciating the subtle difference between local motion and metric expansion. Special relativity tells us nothing can travel through space faster than light. Standing on a planet and firing a rocket, that rocket cannot accelerate past approximately 300,000 kilometers per second, roughly 186,000 miles per second, no matter how much fuel burns. This is a fundamental limit on local motion, on objects traversing space. Metric expansion is different. Space itself, stretching, means distance between 2 points increases without either point actually moving through space. Distant galaxies are not racing away at superluminal speeds through space, but space gets created between us and them faster than light could cross it. This distinction sounds like cheating, like a loophole that should not exist. But it is a fundamental feature of how space-time works according to general relativity. The cosmic speed limit applies to objects moving through space, not to space itself. This has staggering implications for understanding cosmic horizons. Two boundaries will become central to everything that follows. Boundaries often confused with each other, even by people who should know better. And understanding the difference between them is essential to grasping why space-time can be thought of as a prison. The first boundary is called the particle horizon, the edge of the observable universe, the maximum distance from which light has had time to reach us since the early, hot, dense phase following the Big Bang. Think of it as the answer to how far we can see. Approximately 46 billion light-years is the commonly quoted value for the observable universe's radius today, around 4.35 times 10 to the 23rd power kilometers in metric terms, roughly 2.70 times 10 to the 23rd power miles in imperial terms. If the universe is approximately 13.8 billion years old, you might wonder how we can see 46 billion light-years away, since light has only had 13.8 billion years to travel. Expansion explains this. Light from the most distant objects started its journey when those objects sat much closer to us. Over 13.8 billion years of travel, space continued expanding, carrying the source farther away. Asking where that object sits now yields an answer much farther than light travel time would suggest. The particle horizon represents proper distance, distance measured at present cosmic time to the most distant matter from which light has reached us. Everything within this 46 billion light-year sphere is, in principle, visible to us, light received from it, or light we could receive if telescopes were sensitive enough. This is the observable universe, the cosmic stage on which all of astronomy plays out. Here is where things get strange. Being able to see something is not the same as being able to reach it. The second boundary is called the cosmic event horizon, a different kind of limit entirely. It answers a different question. Not how far can we see, but how far can we go? Or, more precisely, how far can light we emit today ever travel, given continued expansion? Approximately 16 billion light-years is the commonly quoted value for the cosmic event horizon, roughly 1.51 times 10 to the 23rd power kilometers in metric terms, about 9.41 times 10 to the 22nd power miles in imperial terms. I remember the first time I truly understood the distinction between these two horizons, and I had to stop and draw it out on paper because my intuition kept rebelling against what the mathematics was telling me. We can see to 46 billion light-years. We can reach only to 16 billion light-years. A vast shell of the observable universe, everything between 16 and 46 billion light-years away, can be observed but never influenced in any way. Think about what that means. Galaxies exist out there right now that we can photograph, whose light we can analyze, whose histories we can study, but to which we could never send a signal, never dispatch a probe, never communicate, regardless of time available or technological advancement. Expansion of space beyond the event horizon proceeds faster than light. Any signal sent today, traveling at maximum possible speed, will never catch up to those distant regions, because space between us and them grows faster than the signal can cross it. The mathematics here is genuinely surprising and worth understanding thoroughly. Let me spend time on the volume calculation. Two spheres need considering. The observable universe, bounded by the particle horizon, has a radius of approximately 46 billion light-years. The reachable universe, bounded by the cosmic event horizon, has a radius of approximately 16 billion light-years. The ratio of these radii is 16 divided by 46, which works out to roughly 0.35. The reachable radius spans about 35% of the observable radius. Thinking in one dimension, you might conclude that about 35% of the observable universe is reachable. We live in three-dimensional space, though, and volume scales as the cube of the radius. The volume of a sphere is 4/3 times pi times the radius cubed. Comparing volumes of two spheres, the ratio equals the ratio of their radii raised to the third power. The fraction of observable universe volume that is reachable equals 16 divided by 46, that whole quantity cubed. Let me walk through this calculation. First, 16 divided by 46 is approximately 0.348. Second, 0.348 cubed is approximately 0.042. That comes to about 4%. Only about 4% of the observable universe's volume lies within the cosmic event horizon. The remaining 96% sits beyond our causal reach. When I first did this calculation, I had to redo it several times because the result seemed wrong. A radius ratio of about 1/3, leading to a volume ratio of about 4%, seemed too extreme. The mathematics is unforgiving, though. Volume scales with the cube of radius, and that cubic scaling amplifies modest differences in radius into enormous differences in volume. A different example puts this in perspective. Imagine two spherical fish tanks, one with a radius of 10 centimeters, the other with a radius of 30 centimeters, 3 times larger. Imagine two spherical fish tanks, one with a radius of 10 centimeters, the other with a radius of 30 centimeters, 3 times larger. How much more water does the larger tank hold? Not 3 times more, not even 10 times more. The larger tank holds 27 times more water, because volume scales as radius cubed, and 3 cubed is 27. The same principle applies to cosmic horizons. The observable universe has a radius about 3 times larger than the event horizon. That factor of 3 in radius translates to a factor of about 27 in volume, meaning the observable universe contains about 27 times more volume than the reachable universe. Flipping this around, the reachable universe contains about 1/27th of the observable volume, roughly 4%. The other 96%, more than 25 times as much volume, lies beyond causal access. Some sources cite 94 or 95% unreachable rather than 96%. This variation arises from slightly different parameter choices, different horizon boundary definitions, or rounding at various calculation stages. The order of magnitude remains robust. Somewhere around 95% of observable volume is causally unreachable. That 95% figure sounds like clickbait, until you understand the cubic relationship. A modest-looking difference in radius, 46 versus 16, translates into an overwhelming difference in volume. The unreachable fraction dominates because volume increases so dramatically with distance. I find this one of the most disquieting facts in all of cosmology. The unsettling part is not that space is large, which is old news. Causal access, our ability to send signals, dispatch probes, or influence events in any way, turns out to be dramatically smaller than what we can already observe. We are not just small in a big universe. We are constrained in a universe we can see but not reach. Let me emphasize what this 95% represents. It is not 95% of empty space. The distant universe fills with galaxies just as our local region does. If the universe is approximately homogeneous on large scales, which observations strongly support, then galaxy density beyond the event horizon matches the density here. Roughly 95% of observable galaxies sit beyond our reach. Hundreds of billions of galaxies lie within the observable universe. 95% unreachable means hundreds of billions of galaxies are visible but forever inaccessible. We can photograph them, analyze their light, study their properties, but we can never send a single photon that reaches them. The remaining 5% or so, galaxies within the event horizon, still number in the tens of billions, an enormous number, far more than humanity could ever explore, but a small fraction of what we can see. A thought experiment might help illustrate the situation. Imagine being an astronomer in the far future, equipped with technology far beyond current capability. Telescopes that can image individual planets around stars in distant galaxies. Instruments that can detect signs of life or intelligence across billions of light years. Surveying the observable universe reveals thousands of civilizations scattered across billions of galaxies. Now imagine trying to communicate with them. For the 5% of galaxies within the event horizon, communication is at least possible in principle. A signal sent after a journey of billions of years would arrive. Conversation would be impossibly slow, spanning many human generations, but it could happen. For the 95% of galaxies beyond the event horizon, communication is impossible. Not difficult, not inconvenient, but fundamentally impossible. No signal sent would ever reach them. They might as well occupy a separate universe for all the interaction you could have. Seeing these civilizations, studying their histories through the light they emit, watching them rise and fall across cosmic time, all of that would be possible. Saying hello would not. Sending a message of warning or greeting or curiosity would not. Connection would be entirely one way, from their past to your present. This describes our actual situation, scaled down to match current technological capabilities. We cannot yet image planets around stars in other galaxies, much less detect distant civilizations. The geometry is what it is, though. Most of what we can see is forever beyond our influence. Perspective using something tangible helps here. Voyager 1, the farthest human-made object from Earth, was traveling at approximately 17.0 kilometers per second as of August 2024, about 38,027 miles per hour. Astonishingly fast by human standards, the result of gravitational assists from Jupiter and Saturn that flung the spacecraft outward with tremendous velocity. 1 light-year spans approximately 9.46 trillion kilometers, or about 5.88 trillion miles. At Voyager 1's current speed, traveling 1 light-year would take approximately 56,000 years. 56,000 years for 1 light-year. The nearest star system, Alpha Centauri, sits about 4 light-years away. At Voyager's speed, that journey would take over 200,000 years. Consider that the cosmic event horizon sits 16 billion light-years away. That is not a destination reachable by traveling fast enough. It is a boundary beyond which even light, traveling at maximum possible speed, cannot carry our influence because space expands too quickly. The contrast between our engineering capabilities and cosmic constraints is stark. Voyager 1 represents one of humanity's greatest achievements in space exploration. Yet, it would take 56,000 years just to cross a single light-year of the 16 billion light-years to the event horizon. And traveling to the horizon would be meaningless anyway, because the horizon itself recedes as space expands. This is not a barrier that better technology could overcome. This is a fundamental feature of space-time geometry that no amount of engineering can circumvent. An analogy might help make this concrete. Imagine standing on a dock with a boat floating in the water some distance away. A powerful transmitter lets you send a radio signal to that boat. Under normal circumstances, radio waves travel at light speed and reach the boat almost instantaneously on human timescales. Now imagine the water between you and the boat flowing outward, away from the dock, like a river current. If the current is slow, your radio signal still reaches the boat easily, traveling faster than the water flows. What if the current gets faster the farther you are from the dock? What if, at some distance, outward flow exceeds the speed of your radio waves? Beyond that point, no signal sent will ever reach a boat, because even though the signal races toward the boat as fast as physics allows, water carries the boat away faster than the signal can close the gap. This is roughly analogous to the cosmic event horizon. The current is the expansion of space. Near us, expansion is slow enough that light easily outpaces it. Beyond a certain distance, cumulative expansion rate exceeds light speed, and no signal emitted can ever catch up. The particle horizon and event horizon represent two fundamentally different limitations on cosmic existence. The particle horizon limits what we can learn about the past, defining the sphere from which information has had time to reach us since the beginning of cosmic history. The event horizon limits what we can influence in the future, defining the sphere to which information we send today can ever propagate. These two spheres have different radii. The particle horizon is larger, about 46 billion light-years. The event horizon is smaller, about 16 billion light-years. The gap between them creates a haunting asymmetry. We can see far more than we can ever touch. Here is where I want you to think carefully about something before I reveal the answer. The radius of the observable universe is about 46 billion light-years. The radius of the reachable universe, defined by the event horizon, is about 16 billion light-years. The ratio of these radii is roughly 16 divided by 46, or about 0.35. What fraction of the observable universe's volume do you think is actually reachable? Take a guess before I continue. Most people, hearing that the reachable radius is about 35% of the observable radius, assume that means about 35% of the volume is reachable. Volume does not work that way, though. Volume scales with the cube of the radius. Tripling a sphere's radius does not triple its volume, but increases it by a factor of 27, 3 cubed. The fraction of observable universe volume lying within the event horizon is approximately 16 divided by 46, that whole quantity cubed. Working out the mathematics yields approximately 0.042, that is, about 4%. Roughly 4% of the observable universe sits within our cosmic event horizon. Roughly 96% lies beyond it. The safest statement, based on verified horizon distances, is that on the order of 95% of observable volume is outside the event horizon-defined reachability region. We are not done, not even close. Everything I have described so far, the horizons, the unreachable 95%, the constraints on causal access, all of this is based on current understanding of cosmic expansion. And that understanding contains a deeply strange ingredient that makes the situation even more restrictive. 1998 brought two independent research teams making a discovery that would earn the 2011 Nobel Prize in Physics. They were studying Type 1a supernovae, a particular class of stellar explosion occurring in binary star systems when a white dwarf, the dense remnant of a sun-like star, accumulates material from a companion star until reaching critical mass and exploding. Type 1a supernovae are useful for cosmology because they have consistent peak brightness. Exploding at roughly the same critical mass, they release roughly the same energy, making them standard candles, objects whose intrinsic brightness is known, allowing astronomers to calculate distance by measuring apparent brightness. The Supernova Cosmology project, led by Saul Perlmutter, and the High Z Supernova Search team, led by Brian Schmidt and Adam Rees, were using Type 1a supernovae to measure expansion history. Observing supernovae at different distances let them see how expansion rate had changed over time. The expectation was decelerating expansion. Gravity, the attractive force between all matter, should slow expansion down. The question was how quickly expansion was decelerating, which would determine the ultimate fate of the cosmos. What both teams found was the opposite. Distant supernovae were dimmer than expected, meaning they sat farther away than a decelerating expansion model would predict. The universe was not slowing down, it was speeding up. This result was so unexpected that both teams initially suspected errors in their data. They checked calibrations, looked for systematic effects, considered alternative explanations. The result held. Independent teams, using independent methods, found the same thing. Expansion is accelerating. Perlmutter, Schmidt and Rees earned the 2011 Nobel Prize in Physics for this discovery. It fundamentally reshaped understanding of cosmic evolution and introduced dark energy as a major component. For our discussion, the key point is this. The cosmic event horizon is not a temporary feature, but a permanent one. In a decelerating universe, given enough time, light could eventually reach anywhere. In an accelerating universe, there are places light will never reach, no matter how long it travels. Scientists call the accelerating agent dark energy. The name is deliberately vague because we do not actually know what dark energy is. We know how it behaves, more or less. We can describe its effects mathematically. Its fundamental nature remains one of the deepest mysteries in physics, though. The most common way to model dark energy in modern cosmology is as a cosmological constant, a term in Einstein's equations representing constant energy density pervading all of space. In the standard lambda CDM model, the current baseline for cosmological research, dark energy is characterized by a parameter called omega lambda. Based on Planck satellite observations, this parameter is approximately 0.6847, with an uncertainty of about 0.0073. What does that number mean? Roughly 68.3% of total energy content is in dark energy form. Let me put the full composition in perspective. According to the Planck collaboration and other precision measurements, approximately 4.9% of the cosmos is normal matter, everything made of protons, neutrons and electrons, all atoms in stars and planets and people. About 26.8% is dark matter, a mysterious substance that exerts gravitational influence but does not interact with light. Approximately 68.3% is dark energy. The stuff we are made of, the stuff we can see and touch and study directly, makes up less than 5% of the cosmic energy budget. The dominant component, dark energy, remains almost entirely unexplained. Here is what dark energy does that matters for our discussion of cosmic horizons. In a universe without dark energy, or with dark energy that decreased over time, the event horizon would behave differently. The boundary of what we could reach might expand over cosmic time as light has longer to travel. The future would, in some sense, remain open to increasing possibilities. Dark energy changes this. With accelerating expansion, the event horizon does not recede. Expansion rate grows, which means distant objects recede faster and faster. The sphere of causal influence is not expanding into the cosmos. It is effectively shrinking, in the sense that more and more of the universe is being carried beyond our reach as time progresses. Another analogy helps describe this. Imagine an airport moving walkway, a very long one, where you stand near the beginning, wanting to reach a friend at the other end. The walkway moves in the opposite direction from where you want to go. Near the beginning, the walkway moves slowly, just a lazy crawl. Walking toward your friend, you make good progress despite the walkway. The strange feature of this walkway is that the farther you get from the start, the faster it moves. Halfway down, it goes at a brisk walking pace. 3/4 of the way, it moves faster than you can walk. At some point, you reach a place where walkway speed exactly matches your fastest possible walking speed. Beyond that point, no matter how hard you try, you cannot make forward progress. The walkway carries you backward faster than you can advance. That point is analogous to the cosmic event horizon. Beyond it, expansion of space exceeds light speed. A light signal trying to cross that boundary is like you trying to walk past that critical point on the walkway. It always moves forward at maximum speed, but the ground beneath carries it backward faster. The analogy is imperfect because light does not try to go anywhere, and space is not literally a moving surface. The intuition transfers, though. A boundary exists beyond which forward motion at any speed cannot overcome the backward drift. Causal limits shape what future astronomy can do. If acceleration persists indefinitely, which the cosmological constant model predicts, distant structures will become increasingly redshifted over extreme timescales. Light from galaxies beyond the event horizon, light emitted long ago when those galaxies were closer, will continue to reach us, but expansion will stretch that light to longer and longer wavelengths. Eventually, after vast eons, that light will redshift into radio waves, then into wavelengths longer than our observable universe, effectively disappearing from view. Future astronomers, billions of years from now, would find themselves in a universe that appears increasingly empty and static. Observable galaxies would be limited to those gravitationally bound to their local group. Everything else would have faded beyond detection, carried away by relentless expansion. This is not merely a limitation on travel, it is a limitation on knowledge itself. The cosmic horizon is not just a boundary for spacecraft and signals, it is ultimately a boundary for understanding. Let me trace how humanity came to understand these cosmic constraints. For most of human history, the night sky appeared eternal and unchanging. Stars wheeled overhead in predictable patterns, the same constellations ancestors saw thousands of years ago. The cosmos seemed static, fixed, a stage on which earthly drama played out, but which itself did not change. 1687 brought Isaac Newton, publishing his laws of motion and universal gravitation, providing a mathematical framework for understanding how objects move and how gravity operates. Newton's gravity worked as an inverse square force. Double the distance, and gravitational pull drops to 1/4. This framework brilliantly explained planetary orbits, moon motions, and comet trajectories, working so well that it formed physics' foundation for over 2 centuries. Newton's framework treated space and time as absolute backgrounds, fixed stages on which physics occurred. Space was just there, infinite and unchanging. Time flowed uniformly forward. Neither participated in the physics, simply providing the arena. Einstein's general relativity, completed in 1915, shattered this picture. In Einstein's framework, space-time is not a static stage, but a dynamic entity that curves in response to mass and energy. And that curvature is what we experience as gravity. More importantly for our discussion, space-time can change, can expand, can contract. It participates in cosmic history, not serving merely as backdrop. Theoretical groundwork for an expanding universe came from Friedmann and Lemaitre in the 1920s. Their solutions to Einstein's equations showed that a static universe was actually unstable. The mathematics naturally produced models where the scale factor, the measure of cosmic distances, changed over time, not as arbitrary additions to the theory, but as direct emergence from general relativity's structure. Hubble's 1929 observations, showing distant galaxies receding with velocities proportional to their distances, brought theoretical predictions into contact with observational reality. The cosmos was not static, it was expanding. Over the following decades, cosmologists developed increasingly sophisticated models of this expansion. The mathematics of the Friedmann-Lemaitre-Robertson-Walker metric became the standard framework for describing cosmic evolution, a metric describing a universe homogeneous and isotropic on large scales that expands or contracts according to specific equations. Within this framework, the concept of horizons became central to understanding our causal place in the cosmos. The particle horizon was recognized as the maximum distance from which light has had time to reach us, a boundary growing over time as the cosmos ages, because light from more distant regions gradually has time to arrive, though the rate of growth depends on expansion history. The event horizon is a subtler concept, depending not on past history of light travel, but on future evolution. If expansion continues accelerating forever, there is a limit to how far light emitted today can ever travel, and that limit defines the event horizon. The distinction between these two horizons became increasingly important as cosmological models matured. By the late 20th century, the language of particle horizons, Hubble radii, and event horizons was standard in cosmological discussions. 1998 changed everything. The discovery of accelerating expansion was not just a refinement of existing models, but a fundamental transformation in understanding. The cosmos was not merely expanding, but expanding faster and faster. Dark energy, whatever it is, had taken control of cosmic evolution. From 2013 to 2020, precision cosmology tightened understanding considerably. The Planck satellite's cosmic microwave background observations, combined with other data sources like baryon acoustic oscillation measurements, refined constraints on cosmological parameters. The lambda CDM model, with its cosmological constant representing dark energy, remained the best fit to the data. Let me share one more personal reflection before we move toward closing. When I first learned about the distinction between the particle horizon and the event horizon, I had a hard time accepting it. My intuition kept rebelling. If we could see something, surely we could reach it eventually. The cosmos would not be so structured as to show us things we could never touch. The mathematics is clear, though, and observations confirm it. The cosmos is structured exactly that way. We can see much more than we can reach. The asymmetry is built into the geometry of expanding space-time. I have come to find a certain peace in this realization. The limits are not arbitrary. They are not imposed by some external authority. They arise from the fundamental structure of space and time, from the way the cosmos has evolved since its earliest moments. They are as much a part of reality as gravity or light. Knowing the limits, mapping them precisely, understanding why they exist, that is its own kind of achievement. We cannot transcend the prison, but we can understand it. We can describe its walls in mathematical detail. We can predict how it will evolve over cosmic time. That understanding holds value. It is, in a sense, the only kind of cosmic legacy we can leave. Not signals that propagate forever, but knowledge accumulated and recorded, understanding achieved and passed down. Let me return to perspective once more, using a thought experiment. Go outside tonight, if weather permits, and look up at the stars. Every point of light you see is relatively close on cosmic scales. Stars visible to the naked eye all sit within a few thousand light-years, deep within the reachable region of the universe. In principle, you could send a signal to any star you can see, and it would arrive eventually. Think about what you cannot see, though. Think about distant galaxies, billions of light-years away, requiring telescopes to detect. Most of those galaxies sit beyond the cosmic event horizon. Light reaching your eyes was emitted when they were closer, and expansion has carried them away since then. They are visible, but unreachable. You are looking at a universe you can observe, but cannot affect. You receive signals from regions that can never receive signals from you. Something both humbling and clarifying lives in this realization. We are not at the center of the universe. We are not in a privileged position. We are not destined to expand across the cosmos. We are inhabitants of a small region of a vast space-time, with hard limits on what we can ever know or influence. Within those limits, though, there is still an enormous amount to explore. The reachable universe, everything within 16 billion light-years, still contains hundreds of billions of galaxies. Even our own galaxy, the Milky Way, contains hundreds of billions of stars and presumably countless planets. Even our own solar system remains largely unexplored. The prison is vast. It is only a prison when you compare it to what lies beyond. Another analogy captures the asymmetry between what we can see and what we can reach. Imagine being in a dark room with a flashlight. The flashlight lets you see objects within a certain range, say 10 meters. That range defines what you can observe. Now suppose your arms are only 1 meter long. You can see objects 10 meters away, but you can only touch objects within 1 meter. A vast region, 9/10 of your visual range, you can observe but cannot touch. The cosmic situation is similar. Our visual range, the particle horizon, is about 46 billion light-years. Our touch range, the event horizon, is about 16 billion light-years. We can see much farther than we can reach. Unlike your arms, which you might extend with tools, the event horizon cannot be overcome with any technology. The numbers are more extreme than my flashlight analogy suggests. It is not that 90% of visual range exceeds reach. Because of cubic scaling of volume, about 95% of observable volume exceeds reach. We can see 25 times more volume than we can ever influence. Let me also address a subtlety that sometimes confuses people: the relationship between distance and time in cosmology. When we say the observable universe has a radius of 46 billion light-years, we are talking about proper distance now. The distance we would measure if we could somehow freeze time and lay out a ruler across the cosmos. This differs from the distance light actually traveled to reach us. Light from the most distant objects we can see has been traveling for almost the entire age of the universe, roughly 13.8 billion years. Light traveled distance is about 13.8 billion light-years. During those 13.8 billion years, though, space expanded. The source that emitted that light, originally much closer, has been carried away by expansion and now sits 46 billion light-years distant. Similarly, when we say the event horizon sits at 16 billion light-years, we are talking about proper distance now. A light signal we emit today, traveling at light speed, will race against expanding space. By the time the signal reaches 16 billion light-years out, space ahead of it will expand faster than the signal can advance, and it will never reach regions currently beyond that distance. These distance measures can be confusing because they differ from intuitive expectations. They are the physically meaningful quantities for understanding causal limits, though. Let me discuss dark energy in more depth, because understanding its nature, or rather our lack of understanding, is crucial to grasping why the cosmic prison exists. We know that dark energy constitutes approximately 68.3% of total cosmic energy content. We know it causes expansion to accelerate. We know it behaves roughly like a cosmological constant, a constant energy density pervading all of space. What we do not know is what dark energy actually is. This is one of the deepest mysteries in physics. We have measured dark energy's effects with high precision. The Planck satellite, observing cosmic microwave background radiation left over from the early universe, has pinned down the dark energy density parameter to remarkable accuracy. The value of omega lambda, approximately 0.6847 plus or minus 0.0073, tells us how much of the cosmic energy budget dark energy claims. Knowing how much dark energy exists does not tell us what it is, though. One possibility is that dark energy really is a cosmological constant, a term Einstein introduced to his equations back in 1917. In this interpretation, empty space itself has a fixed energy density. Even a region with no particles, no radiation, nothing at all, would contain this background energy. As space expands, creating more volume, total dark energy increases proportionally because density remains constant. This interpretation has certain elegance. The cosmological constant is the simplest possible form of dark energy, requiring no new fields or particles, just the fundamental property of space-time itself. It fits the data well. Current observations are consistent with dark energy being a cosmological constant. There is a problem, though. When physicists try to calculate the expected value of the cosmological constant from fundamental physics, they get answers off by roughly a factor of 10 to the 120th power. That is not a small error. It is perhaps the most dramatic discrepancy between theory and observation in all of physics. This discrepancy is called the cosmological constant problem, and it remains unresolved. Some physicists believe it points to fundamental misunderstanding in our theories. Others believe there might be some mechanism, not yet discovered, that cancels out most of the expected vacuum energy and leaves only the tiny observed value. Still others believe the cosmological constant might not be truly constant after all. This brings us to alternative theories of dark energy. Perhaps dark energy is not a cosmological constant, but a dynamic field that evolves over time. These hypothetical fields go by names like quintessence and are characterized by an equation of state parameter describing how dark energy's density changes as the universe expands. For a cosmological constant, this parameter, usually called W, equals -1 exactly. Energy density remains constant as space expands. For quintessence models, W can differ from -1 and might even change over time. If W is less than -1, dark energy's density actually increases as the universe expands. This leads to scenarios called phantom dark energy, where acceleration becomes more and more extreme, potentially leading to a big rip in which accelerating expansion eventually tears apart galaxies, stars, planets, and even atoms. If W is greater than -1, but still negative, dark energy's density decreases over time, but more slowly than matter density. This would still lead to accelerating expansion and an event horizon, but with different detailed behavior. If W changed from less than -1 to greater than -1, or vice versa, the cosmic future could look very different from what we expect. Current observations constrain W to be very close to -1. Planck data, combined with other observations, gives a value consistent with the cosmological constant, to within a few percent. That few percent leaves room for alternative models, though, and distinguishing between possibilities is a major goal of ongoing cosmological surveys. This matters for our discussion of cosmic horizons, because dark energy's nature determines the long-term fate of the event horizon, and thus the ultimate extent of our cosmic prison. Today, this model serves as the working baseline for interpreting most cosmological observations, with accelerated expansion consistent with dark energy-like behavior well established. What remains uncertain is dark energy's fundamental nature. Is it truly a cosmological constant, unchanging throughout cosmic history? Or does it evolve over time? This question impacts the long-term behavior of horizons and remains an active area of research. Large surveys continue pushing measurement precision. Cosmic microwave background constraints from Planck remain foundational. Large-scale structure surveys mapping galaxy distribution are designed to refine understanding of expansion history and test different dark energy models. Regardless of how these details resolve, the basic picture is unlikely to change dramatically. The cosmos is expanding. Expansion is accelerating. Horizons limit what we can see and what we can reach. The reachable fraction of the observable universe is dramatically smaller than most people realize. Let me explore what this means from a slightly different angle. Picture sending a perfectly aimed light signal toward a galaxy lying just beyond the cosmic event horizon. Direction calculated precisely. Signal as focused and powerful as physics allows. The signal releases and begins its journey at light speed. What happens? The signal races outward. For a while, it makes progress, closing distance between starting point and target. The space it crosses expands, though. Because the galaxy sits beyond the event horizon, that expansion proceeds faster than light speed in aggregate. The signal keeps traveling. It never slows down. It never stops. Distance to the galaxy keeps growing faster than the signal can close it, though. The signal is like a swimmer in a river that flows outward faster than they can swim. No matter how hard they stroke, the shore recedes. The signal will travel forever, but it will never arrive. This is not speculation. This is what the mathematics of general relativity, combined with observations of cosmic expansion, tells us must happen, built into the structure of space-time itself. Here is the part I find most haunting. The signal does not know it will never arrive. From the signal's perspective, if a light beam could have a perspective, it is always making progress, always moving forward at light speed through the space immediately around it. Only when you ask about global geometry, about what is happening to space between signal and target, do you see the impossibility. The prison is invisible from inside the cell. Let me now address some counterintuitive aspects of this cosmic situation. Because intuition evolved for dealing with middle-sized objects. Moving at everyday speeds on a planet's surface consistently leads us astray when contemplating cosmological scales. First, the faster-than-light recession. Distant galaxies can recede faster than light speed. This sounds like it should violate the most fundamental speed limit in physics. It does not, and understanding why is essential to grasping the nature of cosmic horizons. Special relativity tells us no object can travel through space faster than light, an absolute limit on local motion. A spaceship with engines firing cannot accelerate past light speed, no matter how much energy expends. Approaching light speed, mass effectively increases, requiring more and more energy to accelerate further. At light speed itself, infinite energy would be required. The barrier is absolute. Metric expansion is different, though. Space itself stretching does not mean objects travel through space at superluminal speeds. Space between objects increases, and this does not violate special relativity because the speed limit applies to local motion, to objects moving through a region of space, not to global behavior of space itself. When we say a galaxy recedes faster than light, we do not mean it zooms through space faster than photons could travel. Space between us and it accumulates faster than light can cross it. The galaxy might sit perfectly still in its local region of space. But total distance between us grows superluminally because so much expanding space lies in between. This distinction might seem like philosophical hair-splitting, but it has observational consequences. It explains why we can see galaxies that are, right now, receding faster than light. We see them because light reaching us left them long ago, when expansion was slower and they were closer. That light has been traveling toward us while space expanded behind it. It is old light, showing those galaxies as they were billions of years ago, not as they are now. Second, we can see what we can never reach. This is the strangest asymmetry in our cosmic situation. The observable universe, defined by the particle horizon, is larger than the reachable universe, defined by the event horizon. We can receive light from regions that we can never send signals to. How is this possible? The key is time. The particle horizon grows as the cosmos ages because light from more distant regions has had time to arrive. We constantly expand the sphere of what we can observe. Light that left a distant galaxy billions of years ago is only now reaching us, adding that galaxy to our observable catalogue. The event horizon is about the future, not the past. It asks, if I send a signal now, how far can it ever get? Because expansion accelerates, there is a limit to how far that signal can propagate. The signal can race outward for billions of years, but space expands faster than it can advance beyond a certain distance. The observable universe keeps growing, incorporating light that has been traveling toward us. The reachable universe, the region we can affect, is constrained by accelerating expansion that prevents our signals from ever reaching distant regions. We inherit light from the past. We cannot bequeath signals to the future, at least not to distant parts of the future cosmos. Pause and absorb that asymmetry. Looking at a galaxy, studying its structure, analyzing light it emitted billions of years ago, knowing with mathematical certainty that no message sent, no matter how powerful, will ever reach it. Connection is one way. We are passive receivers of ancient light from a source forever beyond our influence. This is why space-time can be thought of as a prison. Not because we lack technology to escape, not because distances are merely inconvenient, but because space-time's geometry itself makes certain regions fundamentally unreachable. This is not an engineering problem. This is a feature of reality. Let me also discuss the Hubble tension, because it illustrates that our understanding of cosmic expansion is still being refined. There is a discrepancy between the expansion rate measured from the cosmic microwave background and the rate measured from more local indicators like supernovae and Cepheid variables. This knowledge was not handed to us, but dug out through centuries of effort, building on each generation's work, making mistakes and correcting them, testing ideas against reality. The Casimir effect, vacuum fluctuations, and quantum field theory were all born from similar patient investigation. The cosmic event horizon was predicted theoretically before precise measurements could confirm it. The 1998 discovery of accelerating expansion came from comparing supernova brightness across billions of light years, a feat requiring telescopes, computers, and analytical techniques that did not exist even a few decades earlier. Human curiosity and persistence extended our understanding into realms far beyond everyday experience. We cannot see cosmic horizons directly and cannot experience expansion at cosmic scales, but we found ways to learn about them anyway. This is the part that fills me with wonder. Not just that space-time is a prison, but that we learned this. Equations scribbled on paper predict effects we can then measure. Theoretical speculation about horizons can be constrained by observing the apparent brightness of exploding stars in distant galaxies. The correspondence between theory and reality, the ability of mathematics to capture physical behavior, is not guaranteed. We discovered it again and again at ever larger scales and ever greater distances. Let me talk about what it means for science to have established facts and open questions at the same time. Cosmic expansion is an established fact. It has been measured by multiple groups using multiple techniques. Theory and experiment agree. The physics is well understood. Dark energy's fundamental nature is an open question. It is motivated by observational evidence, constrained by data, but not explained. We know dark energy exists and what it does. We do not know what it is. Horizons are established features of expanding cosmology. Their precise values depend on cosmological parameters that continue to be refined. But their existence follows from the mathematics of general relativity applied to an expanding, accelerating universe. Both of these, established facts and open questions, are legitimate parts of science. Science is not just a collection of known facts, but also a process of investigation, a way of asking questions and seeking answers. Established facts give us confidence. They show that methods work, that theory and experiment can align, that we can understand aspects of reality far from everyday experience. Open questions give us direction. They show where more work is needed, where new ideas might make a difference, where the frontier lies. A healthy science has both. Too much certainty, and there is nothing left to discover. Too much uncertainty, and there is no foundation to build on. Cosmology, with its established framework of expanding space-time and its open questions about dark energy, has both. Let me consider the philosophical implications of what we have discussed. The classical worldview, the one that dominated physics before the 20th century, was mechanistic and deterministic. The universe was a collection of particles moving through empty space according to definite laws. Given initial conditions, everything that followed was determined. Empty space was just the background, the container in which physics happened. General relativity changed this picture. Space-time became dynamic rather than static. It could curve, expand, and contract. The container turned out to have properties that mattered for physics. The discovery of cosmic expansion revealed that space-time is not eternal and unchanging, but has a history. The discovery of accelerating expansion revealed that space-time's future differs from its past. The existence of horizons revealed that space-time constrains not just where we can go, but what we can ever influence. This is a significant shift in how we think about the physical world. The cosmos is not infinitely open to exploration. It has hard limits built into its structure. The container constrains the contents. What does this mean for questions like the ultimate fate of intelligence in the universe? If intelligent life spreads beyond Earth, could it eventually span the cosmos? The geometry of space-time says no, at least not the whole cosmos. At best, intelligence could spread within the event horizon, reaching tens of billions of galaxies over cosmological timescales. Everything beyond that boundary would remain forever out of reach. This places a fundamental limit on cosmic ambition. Not an engineering limit, not a resource limit, but a geometric limit. The prison walls are made of expanding space, and they cannot be breached. I'm not saying this is good or bad, it simply is. Reality has this structure. Our situation includes these constraints. Understanding them is better than not understanding them. Third, what I call the shrinking future communication sphere. In a decelerating expansion universe, the event horizon would recede over time. Light would have more time to travel, more chance to reach distant regions. The sphere of causal influence would grow. Our universe has accelerating expansion, though, which means the opposite happens. Space beyond a certain distance gets carried away faster than light can cross it, and that process intensifies. More and more of the cosmos gets swept beyond reach as cosmic time advances. The timescales involved are vast. We're talking about effects that play out over billions of years. For all practical purposes, on human timescales, the event horizon is stable enough that you do not need to worry about messages being cut off mid-transmission. On cosmological timescales, though, the implication is serious. The set of places we can ever influence is finite and, in a certain sense, shrinking. The cosmic cage is not opening, it is closing. Now, a question often arises when people first learn about cosmic horizons. Does this really matter? We cannot travel to the nearest star, let alone to galaxies billions of light years away. Practical limits on human space exploration are far more restrictive than cosmic horizons. Why care about a boundary 16 billion light years away when we cannot even reach Alpha Centauri? The answer has to do with what horizons tell us about reality's nature, not just practical limitations. Engineering limits are things we might overcome. Better technology, faster rockets, longer-lived spacecraft might someday let us send probes to nearby stars. The limits are severe, but they are, in principle, surmountable. The cosmic event horizon is different. It is not an engineering limit, but a structural feature of space-time. No technological advancement can overcome it, because it is not about traveling fast enough or far enough. It is about space's geometry itself, about how distances change faster than light can cross them. This tells us something about our situation. We are not just small creatures in a big universe. We are causally constrained creatures in a universe that limits what we can influence. The prison is not made of engineering challenges, but of space-time geometry. Horizons also tell us something about existence itself. Regions of the observable universe, regions we can see and study, will never know we existed. Our light will never reach them. Our signals will never arrive. Whatever significance our existence has, it does not extend to those regions. This is humbling. It grounds cosmic ambitions in physical reality. It reminds us that the cosmos is not infinitely open to exploration and influence, but has hard limits built into its structure. Let me talk about what happens at the edges of these horizons, because boundary regions are particularly interesting. Consider a galaxy lying exactly at the cosmic event horizon, 16 billion light-years away. What happens if we try to send a signal to it? The signal leaves Earth, traveling at light speed. It races outward through the expanding cosmos. Year after year, billion years after billion years, the signal covers more and more distance. Space between signal and target galaxy also expands, though. The signal makes progress, but the target recedes. At the event horizon, these two effects exactly balance. The signal approaches, but never arrives. It asymptotically converges on the target, getting infinitely close, but never reaching it. This is a strange kind of boundary. It is not a wall that the signal bumps into. It is a limit that the signal can approach but never cross. The target galaxy is always just out of reach, the gap between signal and target shrinking ever more slowly, but never closing. Now consider a galaxy just slightly beyond the event horizon, 17 billion light-years away. A signal sent toward this galaxy would initially close distance, getting closer and closer. Eventually, expansion of space would win out, though. The signal would reach some maximum penetration and then begin falling back. The target would recede faster than the signal could advance. The signal would continue traveling forever, but it would be carried backward relative to its target. It would end up infinitely far from the galaxy it was trying to reach, not infinitely close, like the signal to the galaxy exactly at the horizon. For a galaxy well beyond the event horizon, the signal would barely make any progress before being swept backward by expansion. The geometry is simply too strongly against it. This behavior at boundaries reveals something important about cosmic horizons. They are not discrete barriers, but smooth transitions. The closer a region is to the event horizon, the longer it takes for signals to give up and fall back. Regions exactly at the horizon represent eternal approach without arrival. Regions beyond represent eventual retreat. Let me discuss what horizons mean for the question of whether life exists elsewhere. If intelligent life exists in the observable universe beyond the event horizon, and statistically there almost certainly is, given the number of galaxies involved, we can never meet them, never communicate with them, never know of their existence except through passive observation. We might see their galaxies in telescopes. We might even, with advanced enough technology, detect biosignatures in atmospheres of their planets, chemicals suggesting biological activity. We could never send them a message, though. We could never receive a reply to any signal we sent. They would be neighbors we can watch, but never visit. Correspondents who can never receive our letters. The cosmos might be teeming with intelligent life, and we might be aware of much of it through observation, while remaining forever isolated from the vast majority of it. This adds another dimension to the loneliness of existence. It is not just that space is large and travel is slow. Most of space is causally disconnected from us, beyond any form of interaction, even in principle, even with infinite time. Let me offer some more numbers and comparisons to help anchor these ideas. The Planck time, the smallest meaningful unit of time in physics, measures 5.39 times 10 to the negative 44 seconds. In 1 second, there are about 1.85 times 10 to the 43rd power Planck times. That is more than a billion, trillion, trillion, trillion Planck times in a single second. The Hubble time, roughly the age of the universe, is about 13.8 billion years. In seconds, that is about 4.35 times 10 to the 17th power seconds. Comparing Hubble time to Planck time gives a ratio of about 8 times 10 to the 60th power. The universe is incomprehensibly older than the Planck time. Yet, even that vast age is not enough for light to reach everywhere in the cosmos. The Planck length, the smallest meaningful distance in physics, measures about 1.616 times 10 to the negative 35 meters. The observable universe's diameter is about 93 billion light-years, which is about 8.8 times 10 to the 26th meters. The ratio is about 5.4 times 10 to the 61st power. The observable universe is incomprehensibly larger than the Planck length. These numbers are so extreme that they require careful thought to appreciate. The cosmos spans ranges of scale that dwarf any everyday comparison, from Planck scales to cosmic scales, from Planck times to cosmic ages. The range of physical reality exceeds our intuitive grasp by many orders of magnitude. Within this vast range, we exist at a particular scale and a particular time. We see a particular portion of the cosmos, bounded by the particle horizon. We can influence a smaller portion, bounded by the event horizon. Our window on reality is vast by human standards, but finite by cosmic standards. This brings me to another thought about perspective. When you look at the night sky on a clear evening, you see a few thousand stars with your naked eye. Those stars are close neighbors, all within a few hundred or a few thousand light years. They sit deep within the reachable region of the universe, comfortably inside the event horizon. With a small telescope, you can see farther. You might spot the Andromeda galaxy, a smudge of light 2.5 million light-years away. Andromeda is gravitationally bound to our Milky Way and will one day merge with it. It too sits well within the reachable region. With larger telescopes, we see much farther. Galaxies, billions of light-years away, appear as faint smears of light. Many of these are beyond the cosmic event horizon. We see them because their light left them long ago, when they were closer and geometry was different. Sending a signal toward them today, that signal would never arrive. The night sky is a mixture of reachable and unreachable. Coast stars we could theoretically visit. Distant galaxies we can only observe. The prison walls are invisible, passing somewhere between familiar neighborhood and remote background. Every photon reaching your eyes has crossed the prison boundary, coming from somewhere within your past light cone. Most of the sources of those photons are now beyond the event horizon, though, carried away by expansion while their light was in transit. You are looking at the past of a universe that is, in its present configuration, mostly beyond your reach. Something humbling and beautiful lives in this realization. Light, you see, is ancient messengers from a cosmos that has moved on. Galaxies you observe have continued their evolution for billions of years since emitting that light. What they look like now, what is happening there today, is forever unknown and unknowable. We are witnesses to a cosmos we cannot touch. The prison walls separate us from most of existence, but they do not block the view. We can see more than we can influence. We can learn more than we can affect. That asymmetry, that strange gap between observation and action, is the essence of our cosmic situation. It is what I mean when I say space-time is a prison. Let me now discuss the scale comparisons once more, because I think they help convey how extraordinary this physics is. The Hubble constant, 67.36 kilometers per second per megaparsec, seems like a small number. At local scales, it is negligible. Earth is not expanding away from the Sun, the solar system is not expanding, the Milky Way is not expanding. Gravitational binding overcomes metric expansion at these scales. Only at scales of millions of light-years and beyond does expansion become the dominant effect. At these scales, galaxies that are not gravitationally bound to each other drift apart, carried by the expansion of space. The current expansion rate implies a Hubble time, the time for a typical galaxy to recede to twice its current distance, of about 14.5 billion years. This is comparable to the current age of the universe, which makes sense because expansion has been happening for most of cosmic history. The acceleration of expansion, driven by dark energy, means that future Hubble times will be shorter. Distant galaxies will recede faster and faster. The event horizon will not recede, and more of the currently observable universe will be carried beyond our reach. On timescales of hundreds of billions of years, the cosmos visible to our descendants, if any exist, will be dramatically different from the cosmos visible to us. Galaxies beyond the local group will have faded from view. The cosmic microwave background will have redshifted to undetectable wavelengths. Evidence of the Big Bang will have been erased. Future cosmologists, if they exist, might look out at a universe that appears to consist only of the merged remnant of the Milky Way and Andromeda galaxies, surrounded by empty space. They would have no way of knowing that the universe was once filled with hundreds of billions of other galaxies, all visible, all accessible to study. We are fortunate to exist during an era when cosmic history is still legible. The evidence is still available. The clues have not yet been erased. This is one of the strange implications of accelerating expansion. The truths we have uncovered are temporary truths, accessible only during a particular window of cosmic time. We are privileged observers, seeing the cosmos in an era of maximum visibility. Knowing this adds urgency to cosmological research. The evidence will not last forever. What we can learn now, we should learn now. Future generations may not have the same opportunity. Let me also address what some physicists find most unsettling about these horizons. The most unsettling part is not that space is big, which is old news. The unsettling part is that causal access, our ability to send signals, dispatch probes, or influence events in any way, is dramatically smaller than what we can already observe. Consider this. We can photograph a galaxy, analyze its spectrum, determine its chemical composition, estimate its mass, study its structure, all from billions of light-years away. We have extraordinary observational power. Our ability to influence that galaxy, to send it a single photon that will ever arrive, is zero. Observation and action are decoupled. We are spectators to most of the cosmic drama, not participants. This decoupling feels wrong to intuition shaped by everyday experience. In daily life, if you can see something, you can usually interact with it. Light brings information about distant objects, and that same path of light suggests a path for interaction. The cosmos breaks this symmetry. Light can reach us from places we can never reach. Some find this distressing, others find it clarifying. I tend toward clarity. It tells us something true about our situation. It grounds our cosmic ambitions in physical reality. It reminds us that the cosmos is not infinitely open to exploration and influence, but has hard limits built into its structure. Knowing is better than not knowing, even when what we learn is constraining. Let me talk about timescales once more, because they matter for understanding what these horizons mean in practice. The event horizon is not closing in on us like walls of a trash compactor. It is moving away, in a sense, because space is expanding. Galaxies near the event horizon are being carried beyond it by expansion, but the event horizon itself is not shrinking in terms of proper distance. What is happening is that more and more galaxies are crossing from inside the event horizon to outside it. As time passes, galaxies that are currently near the event horizon will be carried beyond it. Galaxies currently deep within the event horizon will eventually approach it. On cosmological timescales, tens of billions of years, the observable sky will become increasingly empty as distant structures fade from view. This is not something you need to worry about on human timescales. A galaxy 10 billion light-years away today will not noticeably change its accessibility in the next million years. The effects play out over cosmological time. What matters for human timescales is understanding that the constraints exist, that they are real features of space-time geometry, and that no technology can overcome them. Within those constraints, there is still more to explore than humanity could ever exhaust. Let me share one more thought experiment. Imagine you could live for 1 trillion years. Imagine you had access to technology far beyond anything currently imaginable. Ships that could travel at significant fractions of light speed. Habitats that could sustain human life indefinitely. Communication systems that worked across galactic distances. What could you explore in 1 trillion years? With near light-speed travel, you could cross the Milky Way in about 100,000 years. You could reach the Andromeda Galaxy in about 2.5 million years. You could explore the local group of galaxies in tens of millions of years. With 1 trillion years and near light-speed travel, You could theoretically explore billions of galaxies within the event horizon. You could never explore everything within the horizon, because even 1 trillion years is short compared to cosmic timescales. But you could explore an enormous amount. What you could not do, no matter how long you lived or how advanced your technology, is explore anything beyond the event horizon. Those galaxies are forbidden, not by time or distance or technology, but by the geometry of expanding space-time. The prison is not small, it is unimaginably vast. It is only a prison when you compare it to the even vaster, unreachable cosmos beyond. This thought experiment illustrates the nature of the constraint. It is not about having enough time or enough technology. It is about the fundamental structure of space-time. Some regions are simply beyond reach, regardless of resources. Let me also address one final misconception that sometimes arises. People sometimes think that because we can see galaxies beyond the event horizon, those galaxies must somehow still be connected to us. After all, their light reached us. They are part of our observable universe. We can study them. Does that not imply some form of connection? The connection is one way and confined to the past. Light reaching us from those galaxies carries information about their past, about what they were doing when that light was emitted. It does not create any connection to their present or future. Those galaxies, as they exist now, are beyond our reach. Anything we might want to communicate to them, any signal we might send, will never arrive. The light we receive is a gift from their past, not an invitation to their future. This one-way flow of information defines our relationship with most of the observable cosmos. We are downstream receivers of ancient light, observers of history that has already unfolded, witnesses to events we can never influence. The cosmos shows us more than it lets us touch. That is the strange truth at the heart of our cosmic situation. A final perspective on scale might help crystallize everything we have discussed. The ratio between what we can see and what we can reach is about 3:1 in radius, which translates to about 25:1 in volume. For every galaxy within our reach, there are about 24 galaxies we can see but can never influence. These unreachable galaxies are not empty space. They are full of stars, planets, possibly life, possibly intelligence. They have their own histories, their own futures, their own stories. We can witness fragments of those stories through the light they send our way, but we can never participate in them. The cosmos is generous with its light. It shows us what exists, reveals its structure and history, lets us witness events across billions of years and billions of light years. It is stingy with its future, though. Most of what it shows us is off-limits, visible but unreachable. This asymmetry between vision and touch, between observation and action, defines our cosmic situation. We are beings who can see far more than we can ever affect. Our eyes outreach our hands by a factor of about 25 in volume. Some might find this tragic. I find it clarifying. It tells us what kind of universe we inhabit. It sets the boundary conditions for cosmic aspiration. It reminds us that knowing our limits is itself a form of knowledge worth having. The prison walls are far away. The cell is vast beyond comprehension. We will never explore even a tiny fraction of what lies within our reach. Yet, the walls exist, permanent features of space-time geometry, defining the ultimate boundary of what we could ever touch. That we know this, that we have mapped these walls through centuries of accumulated understanding, is one of the great achievements of human inquiry. We are small, we are constrained, and we are the only beings we know of who understand the nature of our constraints. That understanding is valuable. It is the kind of knowledge that can only be gained through patient observation, careful reasoning, and willingness to accept what reality tells us, even when it is not what we hoped to hear. The cosmos is limitless. Space-time is a prison. Both statements are true, and understanding why they do not contradict each other is understanding something deep about the nature of existence. Let me return to this video's title and explain more precisely what it means. The cosmos is limitless, but space-time is a prison. The cosmos refers to the totality of existence, everything that exists or could exist beyond our horizons. Current observations do not tell us whether this totality is finite or infinite. The universe might extend forever, filled with galaxies and stars beyond count. Or it might be finite, but unbounded, wrapping around on itself like the surface of a higher dimensional sphere. Either way, the cosmos is vast beyond our ability to grasp, and might literally be limitless in extent. Space-time, the framework within which we exist and act, imposes hard limits. The particle horizon limits what we can see. The event horizon limits what we can reach. These are not arbitrary boundaries, but features of geometry, consequences of expansion history and dark energy's nature. We live in a prison made of expanding space. The walls are not close, the cell is vast by human standards. But the walls are there, and they are, as far as we can tell, permanent. This is not a comfortable thought for those who dream of spreading among the stars, of one day reaching across the cosmos, of eventually making contact with other intelligent life throughout the universe. Space-time geometry says, no, most of the cosmos will forever be beyond our reach. Within the prison, there is still much to explore, though. Tens of billions of galaxies lie within the event horizon. Hundreds of billions of stars populate our own galaxy alone. We have barely begun to investigate our own solar system. The prison is not small. It is only a prison when compared to the vastness beyond it. Understanding this, having mapped the horizons and calculated their dimensions and predicted their future evolution, is its own kind of achievement. We are prisoners who comprehend our confinement. Comprehension does not free us, but it does distinguish us. We know where the walls are, even if we can never touch most of them. Let me explore what all of this means for understanding our place in the cosmos. Several facts are now established. The universe is approximately 13.8 billion years old. It expands, and that expansion accelerates, driven by dark energy constituting roughly 68% of the cosmic energy budget. The observable universe extends about 46 billion light-years in every direction. But the reachable universe, bounded by the cosmic event horizon, extends only about 16 billion light-years. Roughly 95% of what we can see is beyond our causal reach. What should we make of this? First, it demands a certain humility about cosmic importance. Not because we are physically small, which is obvious and has been remarked upon for centuries, because our causal reach is so limited. Even if we became a civilization spanning millions of star systems, even if we persisted for billions of years, we would still be confined to a tiny fraction of the observable universe. The prison walls are not close, but they are absolute. Second, it highlights how remarkable it is that we can understand any of this at all. Biological organisms on a small rocky planet can infer the existence of cosmic horizons, can calculate the expansion rate of space, can deduce the presence of dark energy from the dimming of distant supernovae. This is an extraordinary achievement of measurement and reasoning. We are prisoners who have mapped the walls of our cell, even though we can never touch most of them. Third, it raises questions about the entire cosmos beyond what we can observe. Throughout this discussion, I have talked about the observable universe and the reachable universe, both defined relative to cosmic horizons. What about the universe as a whole? Is the cosmos finite or infinite? This is where we must be careful. Horizons tell us about causal access, what we can see and what we can reach. They do not directly tell us about global structure. The cosmos could be infinite, extending forever beyond our horizons, filled with galaxies we will never observe. Or it could be finite but unbounded, curving back on itself like a sphere's surface. Observations establishing horizon physics do not settle this question. The safest framing distinguishes between the cosmos, the totality of existence, and our observable region within it. The cosmos might be limitless in extent, but space-time geometry limits our access to it. We cannot see it all, and we can reach even less. This is the sense in which the title is meant. The cosmos may be limitless, extending without boundary in all directions. Space-time, the framework within which we exist and act, imposes hard limits on observation and influence. We are confined not by walls of stone, but by the geometry of space and time itself. The lambda CDM model, with its cosmological constant representing dark energy, remains the working baseline for cosmological research. Fits the data remarkably well. Planck satellites' cosmic microwave background observations, combined with measurements of baryon acoustic oscillations and gravitational lensing, all point to a universe consistent with this model. Open questions remain, though. The most pressing concerns dark energy's nature. Is it really a cosmological constant, a fixed energy density remaining constant as the universe expands? Or is it something more dynamic, a field that evolves over time? Different answers lead to different long-term fates for cosmic horizons. If dark energy is a true cosmological constant, accelerating expansion will continue indefinitely. The event horizon will remain at roughly current distance. the universe will evolve toward a cold, empty state as galaxies beyond our local group fade from view and stars burn out. If dark energy strengthens over time, acceleration will intensify. The event horizon might shrink, bringing the cosmic prison's walls closer. In the extreme case of phantom dark energy, acceleration could become so violent that it eventually disrupts bound structures at all scales. If dark energy weakens over time, acceleration might eventually stop or reverse. The event horizon might recede, and regions currently beyond reach might someday become accessible. Prison walls might retreat. If dark energy changes sign and becomes attractive rather than repulsive, the universe might eventually stop expanding and begin contracting, potentially ending in a big crunch. Cosmic horizons would evolve very differently in this scenario. Current evidence points toward a cosmological constant, meaning persistent acceleration and a permanent event horizon. Alternatives cannot yet be ruled out, though, and dark energy's nature remains one of the most important open problems in physics. Pause for a moment and think about what it means to live during this particular era of cosmic history. We exist at a time when the observable universe is rich with light. Hundreds of billions of galaxies are visible to our telescopes. We can study cosmic evolution from the earliest moments after the Big Bang to the present day. The cosmos is, in a sense, open to our investigation. This will not always be true. If accelerating expansion continues, future astronomers, billions of years from now, will find themselves in a very different situation. Galaxies beyond our local group will have redshifted out of sight, their light stretched to undetectable wavelengths. The cosmic microwave background will have faded. Evidence of the Big Bang, of cosmic expansion, of the vast universe beyond our immediate neighborhood will have effectively disappeared. Future astronomers might conclude that the universe is small and static, consisting only of the gravitationally bound local group. Evidence we take for granted, evidence telling us about the expanding cosmos and our place within it, will have been erased by the very expansion it documents. This is a strange thought. The truths we have uncovered are, in some sense, temporary truths, accessible only during a particular window of cosmic time. We are fortunate to exist during an era when the cosmos is still visible, when evidence is still available. Let me return to human scale for a moment, because it is easy to lose ourselves in cosmic numbers. 1 light-year spans approximately 9.46 trillion kilometers, or 5.88 trillion miles. A number so large it loses all intuitive meaning. We can say the words, do the arithmetic, but we cannot truly picture 9.46 trillion kilometers. Voyager 1, traveling at 17 kilometers per second, would need 56,000 years to cover that distance. 56,000 years ago, modern humans were sharing the planet with Neanderthals. Agriculture would not be invented for another 46,000 years. Written language would not appear for another 51,000 years. That is, for 1 light year, a distance so small on cosmic scales that it barely registers. Nearest star sits 4 light-years away. The Milky Way spans roughly 100,000 light-years across. The nearest large galaxy, Andromeda, lies about 2.5 million light-years distant. The edge of the observable universe sits 46 billion light-years away. These numbers are not meant to intimidate or overwhelm. They are meant to calibrate. When I talk about the cosmic event horizon being 16 billion light-years away, I am not talking about a distance you could ever travel, even in principle, even with arbitrarily advanced technology. I am talking about a structural feature of space-time that defines the boundary of causal influence. The distance is not inconveniently large. The geometry of expanding space makes it fundamentally uncrossable for any signal we could send. Here is another way to think about our situation. Imagine standing on an island in an endless ocean. From your position, you can see for miles in every direction. On clear days, you can see other islands dotting the horizon. You can study them through telescopes, learn about their shapes and features, watch how they change over time. Now imagine the ocean flowing outward, carrying those islands away. The farther an island sits, the faster the current carries it. Beyond a certain distance, the current is so strong that no boat you could build, no matter how fast, could ever reach those islands. You can see them, but you can never visit them, never communicate with them, never influence what happens there. The visible islands are your observable universe. The reachable islands, those close enough that you could send a boat before the current carries them beyond reach, are your causal future. The current is the expansion of space. This analogy has limits, as all analogies do. The cosmic situation is subtler because light can travel toward us from beyond the event horizon, since that light was emitted in the past, when geometry was different. The core insight holds, though. A vast region exists that you can see but can never touch. Let me draw together the threads of what we have explored. We began with a simple but startling fact. You can see things you can never reach. The observable universe extends approximately 46 billion light-years in every direction, encompassing hundreds of billions of galaxies visible to our telescopes. The reachable universe, bounded by the cosmic event horizon, extends only about 16 billion light-years. Roughly 95% of what we can observe is forever beyond our causal influence. This is not a failure of technology. It is not a limitation we might overcome with better engines or more time. It is a feature of space-time itself, arising from expansion of the universe and, crucially, from acceleration of that expansion driven by dark energy. We traced the history of how humanity came to understand this cosmic structure. From Newton's gravity through Einstein's general relativity, from Friedman and Lemaitre's expanding universe solutions through Hubble's observational confirmation, from theoretical development of horizon concepts to the 1998 discovery of accelerating expansion, we have gradually mapped the walls of our cosmic cell. The mathematics is elegant and merciless. Recession speed scales with distance. Beyond a certain distance, expansion rate exceeds light speed, not because anything travels through space faster than light, but because space itself stretches faster than light can cross it. Signals we send cannot catch up. The boundary is absolute. We explored human scale of these distances. A light year spans 9.46 trillion kilometers. Voyager 1, our fastest spacecraft, would need 56,000 years to travel a single light year. The event horizon sits 16 billion light years away. These numbers are not meant to intimidate, but to calibrate, to give us a sense of the scale of the constraints we face. We discussed dark energy, the mysterious component making up roughly 68% of the cosmic energy budget and driving accelerating expansion. We do not know what dark energy is at a fundamental level, but we know what it does. It ensures that expansion continues to accelerate, that the event horizon remains, that the prison walls are permanent. We reflected on what all of this means for understanding our place in the cosmos. We are not merely small, we are constrained. We exist within a finite causal volume, surrounded by a vast observable sphere that we can see but never influence. The asymmetry between observation and action is built into reality's structure. The cosmos, the totality of existence, might be limitless. Current observations do not tell us whether the universe is finite or infinite in extent. What lies beyond our horizons is, by definition, beyond our knowledge. The cosmos might extend forever, filled with galaxies and stars and phenomena we can never detect. Space-time, the framework within which we exist and act, imposes hard limits on what we can access. Particle horizon limits what we can see. The event horizon limits what we can reach. These are not arbitrary boundaries, but features of geometry, consequences of how the universe has expanded and continues to expand. We are not prisoners in a dungeon. We are inhabitants of a vast region of space-time with walls made of expanding space. The walls are not close, not on any human scale. They are there, though, and they are impassable. I find this picture clarifying rather than depressing, though I understand why reactions differ. It tells us something true about our situation. It grounds cosmic ambitions in physical reality. It reminds us that the cosmos is not arranged for our convenience or aspirations. Within those constraints, there is still so much to explore. The reachable universe is not small. Hundreds of billions of galaxies lie within the event horizon. Billions of stars populate our own galaxy alone. We have barely begun to explore our own solar system. The prison is not a cell. It is a vast territory, more than we could ever exhaust, more than human civilization could fully explore in its entire existence. The limits are real, but so is the opportunity within them. Here is something I want to leave you with. That we can understand any of this is remarkable. We are biological organisms on a small planet orbiting an ordinary star in one of hundreds of billions of galaxies. We evolved to hunt and gather, to navigate local terrain, to form social bonds and recognize faces. Nothing in our evolutionary history prepared us to contemplate cosmic horizons. Here we are, though, using mathematics developed over centuries, observations accumulated with telescopes of increasing power, and reasoning building on the work of countless thinkers, we have mapped the structure of space-time. We have discovered expansion of the universe, existence of dark energy, limits of causal access. We have understood our cosmic prison, even though we can never escape it. That is not nothing. That is an extraordinary achievement of the human intellect. The next time you look up at the night sky, consider what you are seeing. Stars visible to your naked eye are close neighbors, all within the reachable universe. The faint smudge of the Andromeda Galaxy, if you can see it, is light that has traveled 2.5 million years to reach your eyes, from a galaxy gravitationally bound to our own that will one day merge with the Milky Way. Beyond that, beyond what your eyes can detect, lie the distant galaxies populating the observable universe. Most of them are already beyond the cosmic event horizon. Light from them is old light, showing us those galaxies as they were billions of years ago, when the universe was younger and smaller and they were closer than they are now. You are seeing the past of a universe that is, in its present configuration, beyond your reach. Something is profound in that awareness. We are witnesses to a cosmos we cannot touch. We are recipients of light from regions that can never receive our signals. We are observers with limited causal power, but unlimited capacity to understand. If you found value in this exploration, consider subscribing to the channel. There are more journeys like this one, more opportunities to engage with deep questions about space and time and our place within them. These explorations take time to create, and your subscription tells me this work is worth doing. Thank you for taking this time with me. These ideas deserve careful attention, and I appreciate you giving them that. Sleep well tonight, knowing that the stars above you are within reach, at least in principle, while the vast majority of the cosmos lies forever beyond the horizon of what we can ever influence. We are small, we are constrained, and we are the only beings we know of who understand this fact. That understanding is its own kind of freedom. Good night.